So in this video, I will be talking about the number of one bits. I mean the question which was asked in Lead Code February challenge, first problem. So in this problem, it is asked that I have to return the number of set bit. Set bit, I mean the number of one bit. So let's take an example. So if we are given suppose 5, so the binary representation of 5 will be 1 0 1. So there are two set bits, that is one here and one here. So the answer is 2 for 5. So I have to print the number of set bits when presented in binary representation. So there is a brute force approach which is to see all the bits one by one and then checking if it is a set bit or not. If it is a set bit, then we have to increment the counter. Otherwise, continue or till we get the number to be 0. So the brute force will look something like this. So while and I mean uh, we have to continue, till we do not get the value of n to be 0. So now if n and 1, now if my last bit is set, I mean then this if statement will be true. So I will have to increment the counter and I have to shift one bit towards right uh, because I have already taken the last bit into consideration. So this is the brute force approach to uh, travel bits one by one. So this is brute force approach, and the other approach is to use uh, something like this. So here we notice that if we have something like this 1000, there are 30 zeros, 30 times zeros, and after them there is a 1. So I will have to traverse the number 30. I mean I will have to traverse the root 32 times, but there are only uh, there are only two ones. So is there any method to compute this in just 2 times? I mean running the loop for 2 times only. So yeah, there it is. Um, so if we assign the value of n to be n and n minus 1, then this will do our work. I mean, each time it will reduce the rightmost set bit. I mean, each time it will set the rightmost set bit to be 0. So let us take some examples to see that whether this is correct or not. So now suppose I'm given n to be 12. So the binary representation of this will be mm, let us suppose this to be 15. The binary representation will look like this. This is basically 1, 2, 4, and 8. 8 plus 4, 12. 12 plus 1, 13. Okay. So if I do n and n minus 1, what will I get in the first step? N is our 1, 1, 0, 1, and n minus 1 will be 1, 1, 0, 0. And I have to apply AND operation, so I will get 0, 0, 1, 1. So we can notice that the rightmost set bit has been set to 0 here. So the number of bits has been reduced by 1. So now again if we apply n and n minus 1, so this is our n, n minus 1 will be this thing, and I have to perform AND operations. So this will be 0, 0, 0, 1. So again we can notice that the rightmost set bit has been set to 0. So again the number of set bits has been reduced to 1. So we can use, and in the last step we will have something like this and n minus 1. So we will get a 0. So whenever we will get 0, we have to set the loop. So we can use this bitwise manipulation to find the answer. Anyway, there will be no change in the time complexity because in this case we are traversing the whole bit for the number. So the time complexity of this method is O of log base 2n. And here also the time complexity will be O of log base 2n. This is because uh, there can possibility that all the bits are set to 1. So in that case, there will be log n base 2 number of set bits. So I will have to traverse the loop log n base 2 times. So anyway, in some cases, this method is better than this method because we have to traverse only the number of times that bit occurred in the number. So let us look into the code of this problem. So here's the code. I have taken a count variable and set it to be 0. And now whenever we are not getting 0, we have to continue the loop and increment the count variable itself. So whenever we will get 0, I will have to return the count value. So that's it.